Okay, in this video I'd like to talk a little bit more about the difference quotient. I've got two examples I'd like to work through, and they come from homework number 1. This is problem number 10, or at least my example for problem number 10. It says to simplify the difference quotient of this definition for the given function here. For number 12 and other assignments, they use a slightly different form of the difference quotient, so that's what I'll show next. But in this case, we need this one, and to be honest, this is my preferred definition, although Math Excel does explore both of them. So we basically need three parts here. We need f of x plus h, we need f of x, and we need an h value. So a lot of times, especially when I introduce the difference quotient to students for the first time, I like to, just off to the side, kind of illustrate what each of these components are. Well, f of x, that's what was defined over here. F of x is going to be equal to 7x squared minus 8x plus 1. H, of course, is just the letter h. But f of x plus h means to evaluate this function here, as it was defined, not at x, but at x plus h. So everywhere that there was an x, I'm going to change that to x plus h. So I have 7 times x plus h squared minus 8 times x plus h plus 1. And I like to simplify this right away before I even use the difference quotient. So 7 can't be distributed in because the exponent takes precedence. So let's simplify the exponent. That would be x plus h squared, or x plus h times itself. And I'll let my brain relax for a minute while I'm just copying that line. Now I'll do some multiplication. Strictly speaking, we can multiply in from left to right in this group of 3. So I now have 7x plus 7h, x plus h, minus, in this group we distribute in 8x plus, minus 8h plus 1. Now again, I distributed this 7 into this first group, although multiplication is commutative, so you could have squared this together first. So I'm actually going to go back and do that now. I think the distribution is going to be a little bit easier, and it would benefit you in seeing this because this is pretty common practice. So I'm going to ignore the distribution of the 7 for a moment, and I'm going to look at foiling this pair of binomials. We get an x squared for the first products, we get an h squared for the last products, and then in the middle, part of the foiling process, x times h and another h times x. Now order isn't real critical here, but I'll usually write this as x times h, and we actually have 2 of them, so I'm going to record this as plus 2xh plus h squared. Now we can distribute in, and I'll have 7x squared plus 14xh plus 7h squared minus 8x minus 8h plus 1. And so all that preliminary work just pays off because now I don't have to simplify the difference quotient, quotient or fraction. I don't have to simplify all of that algebra inside of the fraction, and instead I can just go straight to the difference quotient. So the difference quotient again requires this f of x plus h to subtract f of x. Well, we already showed what f of x plus h is. That's what this result down here is. So now I'm going to cheat just a little bit since I am using electronic ink, and I'm going to capture all of this stuff. Hopefully all of it comes with it, and we'll drop it in place here. That should have been a 7x squared. All right, so that takes care of f of x plus h. From that, we must subtract f of x. Well, here's f of x. So again, I'm cheating with my electronic ink here. And so now this numerator contains f of x plus h, this group, minus f of x, which is this group, and all of that should be written over h. And so we simplify. Now, there are lots of different ways to do this. We could clear out the grouping symbols, that pair of brackets, or we can just kind of look at this piece by piece and find items that cancel. And this is pretty common in a difference quotient problem, so I'm just going to look to cancel. This 7x squared will subtract this 7x squared and cancel. This negative 8x will subtract another negative 8x, because when you subtract a negative, that's like addition, and those will cancel. And we have now 1 minus 1, which, of course, will cancel. We're left with 14xh plus 7h squared minus 8h all over h. And hopefully you can see what happens next, but I'm going to illustrate this with one additional step. I'm going to factor an h across this numerator. If I factor that numerator by h, I'm left with 14x plus 7h minus 8 over h. And of course, this and this will now factor and cancel. If you're careful, back here you could have seen that each of these three terms in the numerator contained an h and could have been factored back there. But if you're a little rusty from your algebra classes, then I probably wouldn't do that. I would rather see you factor the h in the numerator first and then allow that to cancel like I've done here. And what we're left with is a difference quotient formula that is, I don't know if I should use an equal sign here, I'm just going to use a colon instead. The difference quotient is 14x plus 7h minus 8, which is much more simplified than the definition presented. And as you'll see in future assignments, this is extremely helpful for calculating slopes. We'll talk more about that at another time. Now in this example, we're using a slightly different definition. So I think it's worthwhile to see this, even though I won't require you to use this. If you feel comfortable with it, you're welcome to, but it's not going to be a requirement of mine. So just again to kind of put everything in order, this time we've got 4 components, f of x, f of a, x, and a. Those are the 4 that we've got to worry about. F of x, of course, would be negative 13 over x squared. F of a, so the function f evaluated at a, would be replacing the letter x with the letter a. So f of a is negative 13 over a squared. And then, of course, x and a are just the variables x and a. So as far as our difference quotient this time, let's go with the big fraction. We need f of x minus f of a all over x minus a. Now to make things just a little bit easier, I'm going to note that f of x minus f of a, we're subtracting a negative 13 over a squared. So I'm going to go ahead and change this to just adding 13 over a squared. Now part of the reason why I don't like this definition is we encounter this problem a little bit more frequently, although this is a fraction and we were bound to run into it anyway. But in order to add these two fractions in the numerator of the difference quotient, we've got to find a common denominator. Now the common denominator is going to have to be x squared times a squared. So by multiplying both of these by the opposite or the other fraction's denominator, we should be able to find a common denominator here, and we should be able to add them together. So in this numerator, we now have negative 13a squared over x squared times a squared plus 13x squared over, I'm just going to write this in the same order as the other one, x squared times a squared, and all of that is written as a fraction over x minus a. Well, now we can see that we do have a common denominator, so those two can be added together. Those two fractions can be added together, and we now have negative 13a squared plus 13x squared over x squared a squared and that fraction can be written over x minus a. Now, as a bit of foreshadowing, I noticed that this denominator of the difference quotient has an x minus a, but the numerator of the difference quotient has an a squared plus an x squared. So what I'm going to do is I'm going to erase this numerator and rewrite it so that it's at least in the same order as the denominator, and you'll see why in just a moment. We have 13x squared minus 13a squared now. And now we've got an x squared minus a squared in the same order that we have x minus a. Now I'm going to find a common factor here of 13 and factor that out. And we're left with x squared minus a squared. And hopefully that looks familiar to you. We now have a difference of two squares. And a difference of two squares is easily factorable. X plus a and x minus a. So that fraction is still over x squared times a squared, all over x minus a. All right, so let's focus on this division sign for a second, this larger division, the primary division symbol. Remember, when you have two fractions that are being divided, or two elements that are being divided, say a over b, a fraction divided by some number c, that would be the same as a over b times the inverse, 1 over c. So using that definition of quotients of fractions, we can go ahead and rewrite this expression. X plus a, x minus a over x squared times a squared. So instead of taking this fraction and dividing it by x minus a, we could simply multiply by 1 over x minus a. And now, hopefully you'll notice that this factor x minus a can cancel this factor x minus a. And if we multiply now, well, we've got a placeholder of 1. Multiplying straight across, we're left with 13 times x plus a over x squared times a squared. And that's the result of our difference quotient. We can't simplify any further. Now again, we don't quite see the benefit here because we haven't tied difference quotients to limits just yet. But just to give you a preview and hopefully give you an idea of where we're going next, we would have used this definition of the limit trying to get x and a to be the same number. If x and a are the same number, then when they're subtracted, of course, that'll equal 0, and we can't have that 0 in the denominator. By rewriting the difference quotient in a different form, if x and a are the same number, well, that doesn't necessarily create a problem for us. The only time we would encounter a problem here is that if x and the number a were both equal to 0. But outside of that restriction, then this difference quotient would be helpful for us in our next series of assignments when we start getting into Unit 2. So I know this video was a little bit lengthy, but hopefully that conversation and you being able to watch me work through these two problems and hear my commentary on it might give you a better idea on how to approach the difference quotient. And I assure you shortly, probably even next week, we'll be talking about the applications of the difference quotient, and you'll see why it's so important in the limits unit. Thanks for watching. Let me know if you have any other questions.